I'd now like to talk about some wave properties. And one thing that we know is that small particles that are traveling relatively slowly will actually have measurable waves. They travel in wave shapes. So what we're finding is that light, even though it's a photon, which has no mass, actually has mass as related to the Einstein equation, E equals mc squared. It will travel in this wave shape. So what we find is that light will actually behave as a wave, and it will behave as a particle. And I like to think of light as being a particle that travels in a wave. So let's look at what kinds of things can be observed to travel in waves. If we take a look at an everyday item like a baseball, and we've got it traveling at 10 meters per second, we can measure the wavelength of that wave by using the Broglie wavelength equation. Now the wavelength of a wave is the distance between one crest and another crest of a wave. Actually, it's between any two parts of any two same parts of a wave, but we'll go from crest to crest of a wave. And we notice that for a baseball, if we plug everything in, we've got h, which is Planck's constant, a very small value, 6.626 times 10 to the negative 34 joule seconds. The mass of a baseball is about 142 grams, which is 0.142 kilograms, and we're saying that it's traveling at 10 meters per second. In that instance, we find the wavelength to be 4.66 times 10 to the negative 34 meters. That's a very, very small wavelength. In fact, we can't measure that. And so for everyday objects, even though they do have a de Broglie wavelength associated with them, we can't measure it and we don't notice it for everyday objects. But let's say we've got an electron. Electrons have a mass of 9.11 times 10 to the negative 31 kilograms, a number that's a lot more comparable to the Planck constant that we see here. Even if we make this go really fast at the speed of light, you can see that we end up with a wavelength that's going to be 2.42 times 10 to the negative 12 meters, which is a measurable type wavelength. We can measure wavelengths in this range. So what we're seeing here is that very small particles, even if they're traveling very fast, will have measurable wavelengths. Alright, so let's go back and take a look at wave portions and wave properties. Alright, so this is what a wave looks like. It looks like a sine curve. And let's look at some terms associated with waves. We can talk about crests, which are like mountains, and troughs, which are like valleys. We talk about amplitude sometimes, which has to do with the height of the wave. And we also talk about wavelength, which I've already discussed as being the distance between two of the same section of the wave. In this case, the distance between two hills or peaks, or the distance between two troughs. And we can also talk about frequency. Now, frequency is how the wave is, how many times a wave will pass a point in a given second. I've got this frequency set so that about one wave passes this point every second. So we're talking about maybe a mountain to a mountain or a peak to a peak. So this peak to this peak takes about 1 second. So this wave is running about 1 cycle per second. Now what you've got to understand is that if it's a photon, it's always traveling at the same speed. So the frequency is going to be related to the wavelength. And you can see that if we increase the frequency here, we're going to be seeing probably looks to be about 30, maybe not that many, say about 10 waves per second. So about 10 waves are passing this point every second. And what we're seeing here is that the wavelength is going to shorten because the speed of light is going to remain the same. So let's look at the equation for the speed of light and how it relates frequency to wavelength, and then we can talk about the electromagnetic spectrum in an intelligent way. Alright, so let's look at the formula here. We know that we've got frequency, which has the symbol nu. It's a Greek letter. Right, so nu is what that is supposed to be, and this is wavelength. Which is the Greek letter lambda. Now, frequency and wavelength are related by the speed of light, and what we know is that c, which is the speed of light, is equal to nu times lambda. So what that means is that the frequency is going to equal the speed of light divided by the wavelength. So what we can see here is that there's an inverse relationship. As one increases, one decreases. And we're going to see examples of that when we take a look at the electromagnetic spectrum.